Hey group, let me try another solution here for you. I got a question here about number 13. And it begins off by saying we have a hollow aluminum cylinder that is 20 centimeters deep with an initial capacity of 2 liters at 20 degrees Celsius. All right, so if I kind of draw a picture here, I've got this container. It has some cross-sectional area. And then the height of 20 centimeters. It says it has a volume then of 2.00 liters. So that's the volume of the inside of the container. And in fact, if we wanted to, and I think we're going to need it, so why don't we just do that now, we could figure out the area, because we know that volume is the area times the height of a cylinder. And let's see if we can find the area. The height, they say, is 20 centimeters. Now, there's probably something real important here to remember about a liter. The definition of a liter, if you don't know, is defined as a little cube that is 10 centimeters by 10 centimeters by 10 centimeters. That is the definition of a liter. So 10 times 10 times 10 is 1,000 cubic centimeters is the definition of a liter. So when they say I've got 2 liters, they're also telling me I've got 2,000 cubic centimeters, which then becomes helpful because a centimeter cancels with 1, leaving me square centimeters for the unit of area. And then a 20 goes into here 100 times. And so they have indirectly already told me what the area is. Now, I should say at 20 degrees Celsius. So one thing I hope you're getting out of this chapter about thermal expansion is you can't say how big something is without also saying what its temperature is. Now, these don't change by too much. So, as you know, a lot of times we don't say, hey, my car is, and you give a length, and you don't say what temperature. But technically, it's a little longer when it warms up and a little shorter when it cools down. And so if things are really, accurate and or needed that accuracy, you got to say at what temperature. All right, so it's 20 centimeters tall at 20 degrees Celsius, and it has a area of 100 square centimeters at 20 degrees Celsius. So that's kind of what that first sentence is telling me. And then it says it is completely filled up with turpentine and then slowly warmed to 80 degrees. How much turpentine overflows? Okay, so the increase or the change in volume of the turpentine, and also, for that matter, the change in volume of the aluminum can be calculated here. Because what's going to happen is if you were to fill this container at 20 degrees with turpentine, well, then you would also have 2 liters of turpentine. But as you warm it up, it's going to have a new volume. And so since turpentine is a liquid, I could do something like this. The beta is the expansion coefficient, the volume expansion coefficient for a liquid. Now, the container itself, though, is also going to get a little bit bigger. And the container is made out of a solid, so we don't list the volume expansions for solids. We just list the linear expansion, noting then that 3 times the linear expansion is the volume expansion. So I'll go 3 alpha equals that initial. Okay, so here's where I need to kind of flip over to the book, and I'm looking at table 1 and chapter 19, and I'm scanning the second column, which says turpentine, and it says 9.0 times 10 to the minus 4 inverse degree Celsius. Because the turpentine has 2 liters, or should I do centimeters? Why don't I just do centimeters? So 2,000 cubic centimeters, and we're going to warm it up 60 degrees Celsius. So the degrees Celsius and the inverse degrees Celsius cancel off, and this is going to tell me the increase in volume of the turpentine. So 9 times 10 to the minus 4 times 2,000 times 60, and we're looking at about 108 cubic centimeters is how much bigger the turpentine gets. Okay. The aluminum would be 3 times its linear coefficient, which is 24 times 10 to the minus 6 inverse degrees Celsius. The aluminum also starts off at a volume of 2,000 cubic centimeters. And we're going to also be warming the container. And so again, the degrees Celsius cancels off, and we've got the volume in cubic centimeters. So 3 times 24 times 10 to the negative 6 times 2,000 times 60, and this is 8.64 cubic centimeters. Okay. So the reason the aluminum one is important, because if you just ignored the container, you would say, all 108 of the increased volume of the turpentine would flow over. But it's going to be short of that a little bit because the container actually gets a little bit bigger. So the amount that actually flows over the top would be the difference between these two. The 108 cubic centimeters minus the 8.64 cubic centimeters. And so 108 minus 8.64, and that looks like about a 99, if I go 3 significant figures, 0.4 cubic centimeters. So that's what ends up on the floor. Okay? And so there's the first half. Let me turn off the book and go back to the question. There was a part B here. Okay, so B, if the cylinder is then cooled back to 20 degrees, how far below? So if we hadn't spilled any, it all would have gone back, and the turpentine would have shrunk faster and gone all the way down to 2 liters, and the aluminum would have shrunk and gone all the way down to 2 liters. And, of course, then they'd be a perfect match again. But the fact that this much flowed over the top means we lost some of our turpentine. And we could do this as a percentage or a fraction. So 99.4 cubic centimeters has flown over, is over the edge and sitting on the table or the ground out of the total amount of turpentine that we have, which would be 2,108 cubic centimeters. Okay. Now, that's these are the volumes at warmed up 60, so it's 80 degrees Celsius. So again, remember, you can't talk about a volume unless you also say at what temperature. So when I say 99.4 cubic centimeters float over the top, I'm saying at 80 degrees. And chances are, once it flows over the top, maybe it hits the table and cools down and then contracts a little bit. So that's probably not that much on the table. But anyways, I think what they wanted is how much flows over at that higher temperature. I guess it would start to flow over at a lower temperature. But anyways, so that's this idea. But that's why when I say a fraction and I say 99.4 out of, I don't say 2,000. I say out of 2,100 because, how much of it, flowed over the edge at that higher temperature. So if I go 99.4 and I divide it by 2,108, I could say that 0.4715, if you will, was lost. Almost 5% was lost. Okay. Now, I'm thinking that might be helpful because then, maybe I should have put, this was A, and I'm off to B. But when it all cools down, the aluminum is going to go back to a height of 20 and an area of 100 square centimeters. So the turpentine would be down here in the container, a hair lower, and it would be a hair lower. This fraction lower would be that same amount that was lost. So I could say 0.04715 of 20. You know, what fraction of 20 would it be below? Because this is the fractional loss. And so this would here represent this little top here would represent the amount that is lost. Okay, so let me make that number and multiply by 20. And it looks like we are at a 0.943 centimeters. This would be centimeters. Down below. And I could have done the volume. I was thinking I was going to. That's why I got the area. But I guess thinking of it as a fraction, the fraction of the volume change results right into the fraction of the height change. So I was going to do fraction of volume, and I was going to need the area. But turns out this last step kind of caught me off guard. Yeah, I just really need to do the fraction of the height because the area of the aluminum and the area of the turpentine would be the same. So the fractional loss of volume would be the same as the fractional loss in height. Hope that helps.